Hi and welcome to Unit 1, Topic 3, Video 12. And in this video we're going to look at Example 3, our final example, and prove this rule here. Now of course it's a little bit different to what we've seen. So the first thing I need to do is show you this symbol. And if you haven't seen it before, this means sum of. And it means the sum of this term, 3 to the power of k, for every value from k equals 0 to n minus 1, whatever n is. And we need to show that it's equal to a half times 3 to the power of n minus 1. So what I'm going to do here is I'm going to write this out as an actual question. Because we don't like the sum of rule, it's easier just to deal with the sum as a list. But you can work with the sum of rule, so if you're comfortable, of course, use it by all means. So we start at k equals 0, we get 3 to the power of 0 plus 3 to the power of 1 plus 3 to the power of 2 all the way up to 3 to the power of k, and we want to show that that's equal to, 3 to the power of, not k anymore, n minus 1. We want to show that's equal to a half 3 to the power of n minus 1. Now, I'm going to, hopefully it'll work. It looks tricky. I'm going to start with step 1, and if it does work, it should all fall into place. And we're going to start with n equals 1. And so, n equals 1, the left-hand side is not 3 to the power of 1, because remember we're going up to 3 to the power of n minus 1, and that means we start at 3 to the power of 0. And that, of course, is equal to 1. The right-hand side, and that's equal to a half, so a half times 3 to the power of 1 minus 1, which is a half times 3 minus 1, and that's equal to 1, which is my left-hand side. So we can see that that's worked. Now, I'm going to assume it works for n equals k, and then prove it works for n equals k plus 1, if that's the case. So for n equals k, I get this rule. 3 to the power of 0 plus 3 to the power of 1 plus 3 to the power of 2 plus 3 to the power of k minus 1. So that's where that is, and then that's equal to a half 3 to the power of k minus 1, like that. So that's the assumption step. And now we're going to do the proof step and prove that it works for n equals k plus 1. And so we get 3 to the power of 0 plus 3 to the power of 1 plus 3 squared, oh, that's a 2, squared plus dot 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 plus 3 to the power of k minus 1 plus the next one, which is 3 to the power of k plus 1 minus 1, which simplifies nicely, and we need that to be equal to a half 3 to the power of k plus 1 minus 1. That one doesn't simplify quite as nicely. Now, what I'm going to do here, obviously I'm going to simplify that to 3 to the power of k, but first I'm going to also recognise that this is equal to the assumption step, and therefore I can swap that part of the assumption step in. So my left-hand side is equal to a half 3 to the power of k minus 1 plus 3 to the power of k. And now I'm going to do some expanding out. A half 3 to the power of k minus a half plus 3 to the power of k. Of course, that gives me 1.5 3 to the power of k, which can also be written as 3 over 2 times 3 to the power of k minus a half. And now I can take a half out as a common factor. So it gives me a half 3 times 3 to the power of k minus 1. And 3 times 3 to the power of k is kind of like 3 to the power of 1 times 3 to the power of k. So index law tells me that's 3 to the power of k plus 1 minus 1. And that, of course, is equal to my right-hand side, as required. So now I can make the final statement that I've concluded with the same conclusion we've always used, that therefore, as it works for n equals 1, it must work for n equals 2, as it works for n equals 2, it must work for n equals 3, and so on. And there's our final example of proof by induction. Now, we haven't really delved into this in a lot of detail. This is what we're going to cover in that Unit 1 content. In Unit 3, this comes up again, and we start to look at some trickier ones, maybe where we're dealing with every odd term, 3 to the power of 0, 3 to the power of 1, 3 to the power of 3, 3 to the power of 5, and what that sums to, and how we deal with that. Or maybe one that deals with divisibility. So we'll see those as we get there, but for now, this will cover you for the Unit 1 content that I'd like to see you able to do. All the best.